Hello everybody, my name is Konstantin. I am a PhD student of Peter Richtarik, so this is a paper federated with non-homomorphic encryption. So let me start firstly to motivate why we need federated learning in the first place, and let's just look into classical supervised machine learning. So the classical supervised machine learning, everybody knows this setting, but I will just remind the setting. So what we want to do, we find the f hat, which function approximation, which approximate the real function dependency from xz to y, where z is an observed variable, x is observed variable, y is observed output, based on available data for you. And you can construct your function family class, you can select your regularization strategy, you can construct your loss function. All of these aspects lead to different styles of research. And in practice, the success of applying supervised machine learning, even for fixed tuple xzy, depends on a sample size, signal to noise ratio, your assumption about function family class, and how your assumption is good. And finally, if you really want to use in production machine learning techniques and use function as a predictor, success actually depends on how variable z come into the play on this specific point xy. If you increase function family of the size of the function class, both in theory and practice, you need more samples. One way to mitigate this problem with samples is look into all devices. Let's think about all mobile phones on this planet and ask them to participate in distributed federated learning. And also, we can think about the data set. So in some scenarios, maybe if you're working at some web search company like Google, you can collect the logs of the users and the data is really stored on the server. But there are tons of applications when the data is stored on edge devices in the first place. It's not stored in some database, it's really stored on edge devices. So the goal of federated learning is store data on edge devices and do collaborative machine learning training. However, with this setting, the new challenges come into the place. So the original data distribution XY from previous slide has a one specific distribution D, but in federated learning, clients may have different data distributions. Then device and communication heterogeneity come to the play. The distributed training and control over the participants have also a limited form of federated learning. Next, the communication. If edge devices connected with low bandwidth mobile links, the communication can represent be a bottleneck even for classical machine learning models. And finally, the privacy aspects of the data should be considered as well. Historically, at least like from optimization perspective, the communication challenge can be tackled in 4 different ways, at least for now. You can change topology of the network and do research on this thing. Do more work on each worker, which called like local steps, local optimization, federated learning, and do research on this thing. Perform communication of the compressed messages sent from client to server and do research on this thing. Or perform partial client participation and do research on this thing. So what we found in this paper, and the goal of this paper, is describe that we observed that, in fact, one communication compression mechanism, which originally has been designed to reduce communication, in fact, can be very helpful for privacy guarantees. But firstly, let's take a look into just taxonomy of mechanisms to provide privacy for federated learning. So these days, there are probably main 4 mechanisms. So one mechanism is called trusted execution environments, and it protects execution environment from illegal intervention. So it's almost like an operation system, but it's really implemented in hardware, so it's attempt from people who do chipsets and electronics to limit your ability to, if you don't have these secret keys, to change algorithms which is running inside hardware. Another thing is secure multiparty computation. It protects input of algorithms, however, with the big cost of communication. Another class of algorithms is differential privacy. It protects the output of algorithms in such way that users' data will not be leaked after algorithm execution and reporting the output. The fourth next class of algorithms is homomorphic encryption. So homomorphic encryption is sometimes called crypto magic in cryptography community. If you've never heard about this, you'll like it, I guess. So homomorphic encryption aims to hide plain text input and output from execution part. So with homomorphic encryption, you can hide inputs, give it to another party which perform algorithm execution, which execute it on encrypted data, and if it executes algorithm, it outputs output in encrypted form. Nevertheless, the execution part don't understand what is input, what is output, but it execute correctly if it execute correctly. So in homomorphic encryption, at least two keys should be presented in all schemas. So the public key allow you to perform arithmetic operations on encrypted data. However, without knowing a private key, you cannot unbox this and look into plain text. However, like in this list of four schemas, you don't see any classical cryptography. So, for example, there is a paper from Nature Machine Intelligence, which state that since only certain mathematical operations such as addition, multiplication are homomorphic, the application of homomorphic encryption to neural network requires the operation defined within the algorithm to conform to this limitation, and those standard encryption algorithms like advanced encryption standard IS cannot be used. So it turns out it's not true completely. However, it's not true, but understand how really to use this classical cryptography in the setting in which homomorphic encryption operate. It's also was not so easy for us. Firstly, I'd like to mention that classical cryptography really operates on a binary representation of data, and it's naturally exhibit very poor algebraic properties. So almost no algebraic properties preserved by these block ciphers and symmetric ciphers. So next two slides will be just about background. So if you know about IS block ciphers, you can relax. If you don't know, maybe it gives some context for you. So by itself, IS block cipher maps input block, which is 128 bits, to output block, which is 128 bits, using the secret key, which is 128, 129, 256 bits length, in a stateless deterministic format. You can apply this for encrypt one specific block of bits. However, you cannot apply for a given secret key the block cipher for more than one block. So for two blocks in a specific sense, it's not correct to apply this, and you need to use what's called modes of operations. And it's preserve confidentiality in terms of that you cannot deduce some. You will be protected against chosen plain text attack, which is on the right-hand side. However, confidentiality does not guarantee integrity, and if there is some adversarial guys which want to corrupt actually your data which you transfer, the modes of operation doesn't do this actually. So you need to use integrity, and integrity mechanisms use this message amplification code. The message amplification code is cryptography protected analogous to cyclic redundancy check codes, which is used, for example, in Ethernet frames in network communications. However, the settings, how cyclic redundancy check codes and MAC is defined are different. So for instance, if you have CRC code with R bits, it protects your data stream from any corruption if there is a sequence of burst of incorrect bits of length up to R. So CRC will detect this. And MAC is defined in a sense that without knowing secret key, you actually, without any effective algorithm, you cannot produce even valid tag or this CRC code analog and message pairs. So it's just impossible. But you need to have a secret key. So the most prevalent schema for apply homomorphic encryption in machine learning application is the CKS schema. So CKS schema is called somewhat homomorphic encryption schema because it only operates on specific algebra. It doesn't allow you to express any algorithm with this. So it allows to approximate real and complex dense vectors and operate on them, perform element-wise addition, multiplication, and rotation of elements. You have public keys used to encrypt plain messages, relinearization keys, which is used to reduce error and for technical details inside CKS, and secret key is used to decryption of encrypted messages. The CKS has a specific pipeline. What's important that your input plain message from Rn divided by 2 is really, after a series of encodings, will be, in fact, be encoded as a quotient polynomial ring. So you will have, like, in terms of like just practical implementation, you will have a 2n integers, and each integer will be q bits long. The keys are from quotient polynomial ring of the q xn plus 1, so they will contain n q bits integer number, both public key and secret key. To guarantee this IS-128 capability level, Microsoft Research C library require that n should be greater than 60K and Q should be at least 438 bits long. If you look into some another practical, for example, practical implementation or practical usage of CKS in context of federated learning and the research papers, so you should be careful with this setting because sometimes people want to state, oh, you can use CKS for training deep learning models, machine learning models, but what's a configuration of CKS? This is very important. So really, our discovery start with that. We understand that we need to depart from variance-reduced first-order optimization methods. So if you're not from optimization community, you may not know about this. So in recent years, like 5-6 years, the mechanisms based on variance reduction come into the play. So if you really want to go to solution with very high accuracy, you can decrease your step sizes with scheduling procedures or use specific formulas for this, but there are better mechanisms. However, these better mechanisms, they all involve some notion that the master learn somehow the gradients, local gradients of the clients. And these local gradients of the clients are actually vector of the partial derivatives of the functions, and these partial derivatives actually depends on the data. So you don't want to do this in the first place. So because in our paper, we consider the setting when clients do not trust the master. So we consider distributed compressed gradient descent on the first place. If try to just use, so distributed compressed gradient descent is actually an analog of gradient descent, but before send local gradients to the master, you perform some compression operator, and master, let's say, average all this information from the clients. In our setting, the clients share the secret key. They don't trust channels, they don't trust master, and they don't want to collaboratively train machine learning model. So the good things is that if naively throw ice block cipher in DCGD, so that we start immediately CPACC secure, we are secure against tampering, we solve the problems with untrusted server and channels. But there are a lot of redundancy in this setting. So essentially, DCGD, if try throw naively IS block cipher, master start to be as a communication hub. It obtain encrypted information, encrypted gradients from all clients, and just collect this into the pack and send this back to everybody. And everybody should first unpack this, perform just locally reduction of all obtained information. And there is some hidden redundancy because you can think, oh, the master in some sense should have ability to average obtain the gradients and send less information and broadcast less information to all clients, but the master cannot do this in the first place because clients do not trust him. The time? Okay, I will skip one of last list. Thank you very much. So we used, so we observed that permutation correlated compressors, so which are really designed for communication compressors, can be very useful for provide security. So how much time do I have? It's okay. So with permutation correlated compressors, idea is that the clients flatten all the indices of the gradient, then permute these indices and split into these buckets, and every client work on specific bucket independently. However, the permutation constructed collectively by all clients. So the crucial property is that after this operation, the aggregation actually replaced by concatenation, which is you can do, which is formally like algebraic monoid, not algebraic group, and you don't need to perform any arithmetic. Original DCGD contains some scaling by scalars in the master, but it can be delegated to the clients easily. And one technical thing, like you during use compressors algorithms like PermK, which doesn't depend on the data. In principle, you can use unreliable in privacy sense pseudo-random generator if they're more faster for you because you don't leak any information. So real world scenarios when you can use proposed schema. So for example, individual has several IoT devices. Let's say you have iPhone, iPad, and you want to train a model by utilizing server, but you don't trust this server. So as I said in previous talk, the Google can be central curator and you trust Google, but maybe you don't want to trust Google or anybody. Several companies trust each other, but due to system issues, you still need a central server. However, you don't trust this central server. The GDCKS, so we compared GDCKS with the DCGD PermK IS, and actually the problem starts even with this key sizes. So for example, for IS-128, the key size is 16 bytes, and for HECKS to guarantee IS-128 security level, it's 420 kilobytes. There are numerical issues with GDCKS. The GDCKS specifically work only on FP64 arithmetic, and if you work on very exotic arithmetic representation, or you want to try some exotic arithmetic representation, these IS block ciphers, they are irrelevant for this, so they operate on a bitwise representation. For example, this is an experiment where when we have 50 clients, the dimension of the problem 1,000, number of samples per client is 12, and this is probably just simple linear regression model. And GDCKS require 0.6 10 to the 7 bits per client after first round, and in fact, even already with this amount of information, DCGD PermK IS can already achieve 10⁻20 stationarity level. So in the next experiment, which I present here, so we consider different settings with different dimensions, 1,000 and 1,100K, and in all experiments, the overhead from exploiting HECKS, both in client to master and master to client communication, is thousands more than DCGD PermK IS. There is a very small overhead of applying this IS with the application mode. It's just 32 bytes. So you can observe this difference when your dimension is small, but once your dimension start to be more bigger, there is no overhead in terms of memory footprint during employing IS encryption. So I think I'm already out of time, so yeah. So yeah, thank you very much for your attention. The paper, yeah, will be available. It's available in archive, so totally 56 pages long. In the paper, we have experiment with training ResNet 18, additional discussions, a glossary to support different people with different background, because paper is, in some sense, multidisciplinary. It tried to connect optimization community with cryptography community, and we have also even like emulated systems experiment. So thank you very much for your attention.